A tidal wave. A tidal wave is a shallow water wave caused by the gravitational interactions between the Sun, Moon, and Earth. The rise and fall of the tides play an important role in the natural world and can have a marked effect on maritime-related activities. The image above shows the NOAA San Francisco Tide Station, in operation for more than 150 years. The tidal wave is not related to a tsunami. The gravitational pull of the Sun and Moon on the Earth also causes waves. These waves are tides or, in other words, tidal waves. It is a common misconception that a tidal wave is also like tsunami. The cause of tsunamis are not related to tide information at all but can occur in any tidal state. Tidal waves actually have nothing to do with tides, and nothing to do with ordinary ocean waves. They're more properly called tsunamis, which is Japanese for harbor waves. It's a good name because, although tidal waves lie relatively flat on the open ocean, they can pile up tremendously high when they hit the shallower water of a continental shelf or harbor. Ordinary ocean waves are caused by the action of wind, like ripples on a wind-blown pond. Even the impressive surf of the Pacific got its start as wind blowing across the open water. The height of such waves depends on how fast the wind is blowing, and how much open water the wind travels across. Tsunamis, however, have nothing to do with wind. They're caused by the sudden movement of the Earth's crust during an underwater earthquake or a volcanic eruption. Imagine a child's plastic wading pool filled with water in the backyard. Ordinary waves are like the little surface ripples from the afternoon breeze. A tsunami is what you'd get if you kicked the side of the pool. Tsunamis can travel thousands of miles, and still send water crashing 100 feet high into a harbor or coastal town. A 1960 earthquake in Chile sent tsunamis across the Pacific at 300 miles per hour, destroying harbors in Hawaii and Japan. A tidal wave is a regularly reoccurring shallow water wave caused by effects of the gravitational interactions between the Sun, Moon, and Earth on the ocean. The term tidal wave is often used to refer to tsunamis. However, this reference is incorrect as tsunamis have nothing to do with tides. When used in association with water, the term current describes the motion of the water. Some currents you may be familiar with are the motion of rainwater as it flows down the street, or the motion of the water in a creek, stream, or river flowing from higher elevation to lower elevation. This motion is caused by gravity. The speed and direction, velocity, of currents can be measured and recorded. Oceanic currents are driven by several factors. One is the rise and fall of the tides, which is driven by the gravitational attraction of the Sun and Moon on Earth's oceans. Tides create a current in the oceans, near the shore, and in bays and estuaries along the coast. These are called tidal currents. Tidal currents are the only type of currents that change in a very regular pattern and can be predicted for future dates. A second factor that drives ocean currents is wind. Winds drive currents that are at or near the ocean's surface. These currents are generally measured in meters per second or in knots. 1 knot equals 1.15 miles per hour or 1.85 kilometers per hour. Winds drive currents near coastal areas on a localized scale, and in the open ocean on a global scale. A third factor that drives currents is thermohaline circulation, a process driven by density differences in water due to temperature, thermo, and salinity, haline, in different parts of the ocean. Currents driven by thermohaline circulation occur at both deep and shallow ocean levels and move much slower than tidal or surface currents. The currents tutorial is an overview of the types of currents, what causes them, how they are measured, and how they affect people's lives. Tidal currents occur in conjunction with the rise and fall of the tide. The vertical motion of the tides near the shore causes the water to move horizontally, creating currents. When a tidal current moves toward the land and away from the sea, it floods. When it moves toward the sea away from the land, it ebbs. These tidal currents that ebb and flood in opposite directions are called rectilinear or reversing currents. Rectilinear tidal currents, which typically are found in coastal rivers and estuaries, experience a slack water period of no velocity as they move from the ebbing to flooding stage. And vice versa. After a brief slack period, which can range from seconds to several minutes and generally coincides with high or low tide, the current switches direction and increases in velocity. Tidal currents are the only type of current affected by the interactions of the Earth, Sun, and Moon. The Moon's force is much greater than that of the Sun because it is 389 times closer to the Earth than the Sun is. Tidal currents, just like tides, are affected by the different phases of the Moon. When the Moon is at full or new phases, tidal current velocities are strong and are called spring currents. When the Moon is at first or third quarter phases, tidal current velocities are weak and are called neap currents. Animation of the relationship between vertical and horizontal components of tides. The elliptical orbits of the Moon around the Earth and the Earth around the Sun have substantial effects on the Earth's tides and the currents they produce. Also similar to tides, tidal currents are affected by the relative positions of the Moon and Earth. When the Moon and Earth are positioned nearest to each other, perigee, the currents are stronger than average and are called perigene currents. When the Moon and Earth are at their farthest distance from each other, apogee, the currents are weaker and are called apogean currents. The shape of bays and estuaries also can magnify the intensity of tides and the currents they produce. Funnel-shaped bays in particular can dramatically alter tidal current magnitude. The Bay of Fundy in Nova Scotia is a classic example of this effect, and has the highest tides in the world over 15 meters. Coastal currents are intricately tied to winds, waves, and land formations. Winds that blow along the shoreline, longshore winds, affect waves and, therefore, currents. Before one can understand any type of surface current, one must understand how wind and waves operate. Wave height is affected by wind speed, wind duration, or how long the wind blows. And fetch, which is the distance over water that the wind blows in a single direction. If wind speed is slow, only small waves result, regardless of wind duration or fetch. If the wind speed is great but it only blows for a few minutes, no large waves will result even if the wind speed is strong and fetch is unlimited. Also, if strong winds blow for a long period of time but over a short fetch, no large waves form. Large waves occur only when all three factors combine. Duxbury, et al., 2002. As wind-driven waves approach the shore, friction between the seafloor and the water causes the water to form increasingly steep angles. Waves that become too steep and unstable are termed breakers or breaking waves. By longshore currents is the speed at which waves approach the shore depends on seafloor and shoreline features and the depth of the water. As a wave moves toward the beach, different segments of the wave encounter the beach before others, which slows these segments down. As a result, the wave tends to bend and conform to the general shape of the coastline. Also, waves do not typically reach the beach perfectly parallel to the shoreline. Rather, they arrive at a slight angle, called the angle of wave approach. When a wave reaches a beach or coastline, it releases a burst of energy that generates a current, which runs parallel to the shoreline. This type of current is called a longshore current. Longshore currents are affected by the velocity and angle of a wave. When a wave breaks at a more acute steep angle on a beach, encounters a steeper beach slope, or is very high, longshore currents increase in velocity. Conversely, a wider breaking angle, gentler beach slope, and lower wave height slows a longshore current's velocity. In either case, the water in a longshore current flows up onto the beach, and back into the ocean, as it moves in a sheet formation. As this sheet of water moves on and off the beach, it can capture and transport beach sediment back out to sea. This process, known as longshore drift, can cause significant beach erosion. Rip currents is a dangerous currents were taken at public swimming beaches. As longshore currents move on and off the beach, rip currents may form around low spots or breaks in sandbars, and also near structures such as jetties and piers. A rip current, sometimes incorrectly called a rip tide, is a localized current that flows away from the shoreline toward the ocean, perpendicular or at an acute angle to the shoreline. It usually breaks up not far from shore and is generally not more than 25 meters or 80 feet wide. Rip currents typically reach speeds of 1 to 2 feet per second. However, some rip currents have been measured at 8 feet per second faster than any Olympic swimmer ever recorded, NOAA, 2005b. If wave activity is slight, several low rip currents can form, in various sizes and velocities. But in heavier wave action, fewer, more concentrated rip currents can form. When waves travel from deep to shallow water, they break near the shoreline and generate currents. A rip current forms when a narrow, fast-moving section of water travels in an offshore direction. Rip current speeds as high as 8 feet per second have been measured faster than an Olympic swimmer can sprint. This makes rip currents especially dangerous to beachgoers, as these currents can sweep even the strongest swimmer out to sea. Because rip currents move perpendicular to shore and can be very strong, beach swimmers need to be careful. A person caught in a rip can be swept away from shore very quickly. The best way to escape a rip current is by swimming parallel to the shore instead of towards it, since most rip currents are less than 80 feet wide. A swimmer can also let the current carry him or her out to sea until the force weakens, because rip currents stay close to shore and usually dissipate just beyond the line of breaking waves. Occasionally, however, a rip current can push someone hundreds of yards offshore. The most important thing to remember if you are ever caught in a rip current is not to panic. Continue to breathe, try to keep your head above water, and don't exhaust yourself fighting against the force of the current. Winds blowing across the ocean surface often push water away from an area. When this occurs, water rises up from beneath the surface to replace the diverging surface water. This process is known as upwelling. Upwelling occurs in the open ocean and along coastlines. The reverse process, called downwelling, also occurs when wind causes surface water to build up along a coastline. The surface water eventually sinks toward the bottom. Subsurface water that rises to the surface as a result of upwelling is typically colder, rich in nutrients, and biologically productive. Therefore, good fishing grounds typically are found where upwelling is common. The rich fishing grounds along the west coasts of Africa and South America are supported by year-round coastal upwelling. Seasonal upwelling and downwelling also occur along the west coast of the United States. In winter, winds blow from the south to the north, resulting in downwelling. During the summer, winds blow from the north to the south, and water moves offshore, resulting in upwelling along the coast. This summer upwelling produces cold coastal waters in the San Francisco area. Contributing to the frequent summer fogs, Duxbury, et al., 2002. Coastal currents are affected by local winds. Surface ocean currents, which occur on the open ocean, are driven by a complex global wind system. To understand the effects of winds on ocean currents, one first needs to understand the Coriolis force and the Ekman spiral. If the Earth did not rotate and remain stationary, the atmosphere would circulate between the poles high-pressure areas and the equator a low-pressure area in a simple back-and-forth pattern. But because the Earth rotates, circulating air is deflected. Instead of circulating in a straight pattern, the air deflects toward the right in the northern hemisphere and toward the left in the southern hemisphere, resulting in curved paths. This deflection is called the Coriolis effect. It is named after the French mathematician Gaspard Gustave de Coriolis (1792–1843), who studied the transfer of energy in rotating systems like water wheels. Surface ocean currents and trade winds. Atmospheric circulation and the Coriolis effect create global wind patterns, including the trade winds and westerlies. In the northern hemisphere, warm air around the equator rises and flows north toward the pole. As the air moves away from the equator, the Coriolis effect deflects it toward the right. It cools and descends near 30 degrees north latitude. The descending air blows from the northeast to the southwest, back toward the equator. A similar wind pattern occurs in the southern hemisphere. These winds blow from the southeast toward the northwest and descend near 30 degrees south latitude. These prevailing winds, known as the trade winds, meet at the intertropical convergence zone, also called the doldrums, between 5 degrees north and 5 degrees south latitude, where the winds are calm. The remaining air that does not descend at 30 degrees north or south latitude continues toward the poles and is known as the westerly winds, or westerlies. The trade winds are so named because ships have historically taken advantage of them to aid their journeys between Europe and the Americas. Global winds drag on the water's surface, causing it to move and build up in the direction that the wind is blowing. And just as the Coriolis effect deflects winds to the right in the northern hemisphere, and to the left in the southern hemisphere, it also results in the deflection of major surface ocean currents to the right in the northern hemisphere in a clockwise spiral, and to the left in the southern hemisphere in a counterclockwise spiral. These major spirals of ocean-circling currents are called gyres and occur north and south of the equator. They do not occur at the equator, where the Coriolis effect is not present. There are 5 major ocean-wide gyres: the North Atlantic, South Atlantic, North Pacific, South Pacific, and Indian Ocean gyres. Each is flanked by a strong and narrow western boundary current, and a weak and broad eastern boundary current. One particularly powerful western boundary current is the Gulf Stream. The Gulf Stream, paired with the eastern boundary Canary Current, flanks the North Atlantic gyre. The Gulf Stream, also called the North Atlantic Drift, originates in the Gulf of Mexico, exits through the Strait of Florida, and follows the eastern coastline of the United States and Newfoundland. It travels at speeds of 25 to 75 miles per day at about 1 to 3 knots, 1.15 to 3.45 miles per hour, or 1.85 to 5.55 kilometers per hour. It influences the climate of the east coast of Florida, keeping temperatures warmer in the winter and cooler than the other southeastern states in the summer. Since it also extends toward Europe, it warms Western European countries as well. The Ekman spiral is a consequence of the Coriolis effect. When surface water molecules move by the force of the wind, they, in turn, drag deeper layers of water molecules below them. Each layer of water molecules is moved by friction from the shallower layer, and each deeper layer moves more slowly than the layer above it, until the movement ceases at a depth of about 100 meters or 330 feet. Like the surface water, however, the deeper water is deflected by the Coriolis effect to the right in the northern hemisphere and to the left in the southern hemisphere. As a result, each successively deeper layer of water moves more slowly to the right or left, creating a spiral effect. Because the deeper layers of water move more slowly than the shallower layers, they tend to twist around and flow opposite to the surface current. Thermohaline circulation begins in the Earth's polar regions. When ocean water in these areas gets very cold, sea ice forms. The surrounding seawater gets saltier, increases in density and sinks. Winds drive ocean currents in the upper 100 meters of the ocean's surface. However, ocean currents also flow thousands of meters below the surface. These deep ocean currents are driven by differences in the water's density, which is controlled by temperature, thermo and salinity haline. This process is known as thermohaline circulation. In the Earth's polar regions, ocean water gets very cold, forming sea ice. As a consequence, the surrounding seawater gets saltier, because when sea ice forms, the salt is left behind. As the seawater gets saltier, its density increases, and it starts to sink. Surface water is pulled in to replace the sinking water, which in turn eventually becomes cold and salty enough to sink. This initiates the deep ocean currents driving the global conveyor belt.